Very good evening to everyone, and welcome to the NPTEL 6 live interactive session on the course Mechanical Behavior of Materials Part 1. The course instructor for this course are Dr. Shashank Shekhar and Dr. Sudhanshu Shekhar Singh from the Department of Material Science and Engineering at IIT Kanpur. And myself, Shivam Jaiswal. I am an additional TA. I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So in this live interactive session, we will be going to solve some samples problem related to your weekly content, which will in turn will help you to solve your weekly assignments. Okay. So in this today's live interactive session, we will quickly recapitulate the what are the things has been covered in week 6, and followed by the some concept related question. And if time permits, we'll try to solve the assignment 6 as well. So let's begin. So last week, that is week 6, we started with the concept known as a real dislocation. In the lectures, you have seen the image where the dislocations are curved, not a straight line, but nothing but they are curved. So can the real dislocation can be curved? So can be curved. So the answer is yes. So also let's see. So suppose if we have a both edge and screw dislocation at the same time in our material. So let me draw. Okay, so this is our extra half plane or edge dislocation. Okay, so this is the line vector, and let's say this is our Burgess vector. Okay, and here we have a screw dislocation. So this dislocation line will travel something like this. So here, if we see, we have a dislocation something like this. Okay, let's say this is our point A and this is our point B. So, and suppose this is the direction of Burgess vector. Okay, so if we draw a tangent at point A, this will give the line vector at A, and if we draw a tangent at B, so this will give the line vector at B. So now if we see here, we can say that at point A, U is parallel to Burgess vector. That is, line vector is parallel to Burgess vector. So this is nothing but a screw dislocation, and at point B, U is perpendicular to B vector. So this is nothing but a pure edge dislocation, and previous one was the pure screw dislocation. So this is edge dislocation. Okay. So this is we have talked about this real dislocation, whether they can be bent or not. Okay. So the answer is yes, this can be bent, and it is the mixed dislocation. That is, this dislocation is mixed dislocation. So this is all about the real dislocation. Then after that, we have seen some fundamental characteristics of the dislocation. So what are the fundamental characteristics of dislocation? Like in this, we have seen whether the how the dislocation can terminate inside a crystal. So we have seen that dislocations lines can terminate in only three ways inside a crystal. So what are these three ways? By which three ways the dislocation can terminate inside a crystal? So one is surface. Second one is by branching out of the dislocation, and third one is the loops. Okay. So these are the three fundamental characteristics of these are the three ways through which dislocation can terminate inside a crystal. So the second characteristic is that dislocation cannot terminate inside a crystal. This is the second fundamental. Third one is that vector for given dislocation remains constant irrespective of the orientation of the dislocation. Okay, as in the previous case, we have seen in the real dislocation, in the mixed dislocation, the vector moving downwards, and for the screw dislocation and the edge dislocation, it was same. So in this direction of the dislocation, the Burgess vector remains same. Burgess vector for a given dislocation remains constant irrespective of the orientation of the dislocation. This was the third fundamental characteristics of dislocation. Then we have seen that the dislocation vectors is conserved, like suppose this is one dislocation, it is B1, and if it is branching out in two, let's say this is B2 and this is B3. So B1 should be equal to B2 plus B3, or we can write summation of Burgers vector should be 0. Okay. So this was about the dislocation vectors need to be conserved. Okay. So after this, we have seen some dislocation property for the edge and screw, and what are the conditions for them, or in simple word we can say we have differentiated the edge and screw dislocation. So let me draw the table. So the first thing in the dislocation property that we have considered was the relation between the line vector and the Burgess vector. So and Burgess vector. So in edge dislocation, the line vector is perpendicular to the Burgess vector, and whereas in the screw dislocation, the line vector is parallel to the Burgess vector. So U is perpendicular to Burgess vector and U vector is parallel to Burgess vector. Okay. So now the second property that we studied was the slip direction. So in edge dislocation, slip direction is parallel to Burgess vector, and similarly it is also parallel in screw dislocation as well. Okay, so this is about the slip direction. The third thing that we have seen is the direction of the dislocation line movement. So how does the dislocation line moves? Okay, so in the like in the edge dislocation, it moves parallel to Burgess vector, or it is perpendicular to your line vector. Similarly, in case of screw dislocation, it is perpendicular to Burgess vector, or simply we can say it is always perpendicular to the line vector. Or perpendicular to line vector. So remember, the direction of dislocation line movement is always perpendicular to your line vector. So then we have differentiated the negative and positive dislocation and whether they are physically distinct or not. So positive and negative dislocations. So these are for the edge dislocation, and right hand screw and left hand screw are for the screw dislocation. So the edge dislocation, they are not physically distinct, means depending on the sign convention, the positive and negative edge dislocation changes. So but in the screw dislocation, it is physically distinct. Okay, it will always be the right hand screw and it will always be remain the left hand screw. So and these are physically And fifth thing that we have seen, like what are the processes through by which the dislocation can leave a slip plane. So this we have not studied in detail, but just for your rough idea. So I am writing it down. So in edge dislocation, in edge the dislocation may leave the slip plane by the process known as climb, and in case of screw, it is known as cross slip. Okay. So these are the some basic differences between the edge and screw dislocation. Okay. Then we have seen the dislocation. So suppose if the dislocations are in the loop, all right. Suppose this is the one loop. Okay. And this is the direction of Burgers vector, and it is gliding on the this. Let's say it is gliding on this slide. Okay. So this is the glide direction. Okay. Okay. So or so this is our dislocation, and this is the Burgers vector. Sorry. So this is the Burgess vector, direction of the Burgess vector. So if we take a 4-point, this is, let's say this is A, B, C, and D. So, and if we draw the tangent to the this line vector, line vector, so we'll get something like this. So here we can see that at A and C, the Burgess vector is perpendicular to line vector. So these are the edge dislocation. And this is and point B and D Burgess vector is parallel to line vector. So these are nothing but a screw dislocation. So only the sign will be different. Let's say this is suppose this will be the edge dislocation. Suppose if it is moving in the plane or out of the plane, or it is moving in the slide or out of the slide. So then in that case, let's say this is the dislocation loop. This is the direction of the Burgess vector, whether it is moving in the plane or out of the plane. Then in this case, the Burgess vector is always be perpendicular to the line. So the dislocation will be the edge dislocation throughout. So this is the Burgess vector. So this all dislocation at all point. So it will be nothing but a edge dislocation throughout. And these loops are known as the prismatic loops. So this was about the dislocation loop. Then we came to the concept, like we studied the concept, that is the Volterra construction. So in Volterra construction, what we assume? We assume the one hollow cylinder, and we cut it from the one side, and then we translated in the x, y, and z direction, and then we studied the what are the uh, means which translation in x, y, z gives the which types of dislocation that we have seen. Also, we have seen the angle. If we open that cylinder, angle means by some angle. So some angular opening will be there, and what are they known as? They are known as nothing but a disclination. So disclination. When we will get the disclination, when we will do the angular opening, and the dislocations when we will get a dislocation when we do the translation, that is away from the core. Okay, so let me draw the diagram. So let's say this is the hollow cylinder. X, let's say this is y direction, and this is z. Okay, so suppose if I cut this cylinder from this place, okay, that blue one, and okay, suppose I cut this cylinder from this blue place and stick it together, and then if I move it slightly in the y direction, so what I will get? So I will get a structure something like this. Like so, this is the direction of my line vector, and this gap is let it be just vector. This is the direction of our Burgess vector. So, vector is the direction of the Burgess vector. So here you can see that the Burgess vector are perpendicular to each other. So this is nothing but a dislocation. Okay. Now, so what will happen if we move it in the x direction? So suppose if we move it in the x direction, so so this displacement, let's say it's b. This is the direction of my Burgess vector, and this is the direction of my line of sense vector. So in this case also Burgess vector is perpendicular to the line of sense vector. So this is nothing but again a case of H dislocation. Okay, now what will happen if we move it in the Z direction. So let's say okay. Sorry. So here, this much displacement has occurred, and this displacement is equivalent to B, and this is the direction of the Burgess vector, and this is the direction of the line or sense vector. So in this case, the line vector and sense vector both are parallel to each other. So this is nothing but a case of screw dislocation. So after this, we have seen like what will happen if this is the cylinder and if you open it angularly. So some angular tilt will be there. Like these faces will not be parallel to each other exactly in that case. So in that case, we will get a disclination. Okay. So this is about the Volterra model, and then we studied the stress and strain field around the dislocation, how the stress is generated and what type of stress are there in the edge dislocation and screw dislocation that we have studied. So first we will discuss about the stress field around the screw dislocation. So before going further, let me ask you a question. If in the edge dislocation, we are adding the extra half plane, so what will be the nature of the stress? Whether it is compressive on the plane where we have inserted the extra half plane, and below that. Anyone? So for your better understanding, I will draw the figure and please try to answer it. So let's say this is my extra half plane. Okay. So it is bending something. So now try to answer whether at that extra half plane which type of stresses will be acting. So here, as we are inserting the extra half plane, so it will try to compress the atoms near to each other, and whereas it will at the downside where the extra half plane is missing, it will try to pull two atoms together. So here it will be the tension, and here it will be the compression. Like and the top it will be compressive stresses will be acting, and in the bottom tension stresses will be acting. So if we represent it, so this is the negative stresses, compressive, and this is the positive, that is the tensile stresses. Okay. So this is the some quick introduction of the stresses inside a that causes due to the dislocation. So now moving towards our the point, that is the screw dislocation. So let me draw the cylinder for the Volterra model that we have used. So let's say this is the cylinder. Okay. And this displacement is B. This is direction Z. This is nothing but our axis X. This is Y, and the radius of the cylinder is suppose in the radius at some distance R, and there is some point as distance with an angle at an angle theta and coordinate xi, comma yi. So here you can see that the Burgess vector is parallel to the line vector. So this is the screw dislocation. So now if I unwrap this sheet, okay. So if there is no dislocation, so how should be like this? So it should be like a rectangle, perfect rectangle. So let's say so when there is no dislocation or the no displacement in the z direction, so if I unwrap it, it should be like a rectangle. But what is happening here? Some displacement is there in the z direction, and that is causing to unwrap this sheet like this one, like it is following this green path. Okay, and this distance is nothing but a B, and the length of sheet will be the 2 pi r, and the point is at a distance of theta into r. Okay, so now if we take a displacement in x and y, so it is 0. So ux equal to 0. Similarly, uy equal to 0. But uz is not 0, and it is equal to theta r upon 2 pi r into b. So this r gets cancelled out, and we remain with the theta b upon 2 pi r. Okay, b, that is the b theta upon 2 pi, we can say, and that theta is nothing but a tan inverse of y by x. So we can write b theta upon 2 pi tan inverse of y upon x. Let's say yi upon xi. So similarly, as there is a no displacement in uy and the in uy direction, so the strain in the u and y direction will be 0. So exx equal to eyy equal to ezz equal to EXY equal to EYX equal to 0. Okay. So no, only the displacement is in the shear form. So that is the only the shear strain is acting. No normal strain is. All the normal strains are 0, and the shear strain in XY and YX direction is also 0. So only we are left with EXZ equal to EZX equal to is half of your shear strain. So it is dou UZ upon dou X plus dou U X upon dou Z. So here, as the UX is 0, this whole terms becomes 0. So now we are only left with the dou U by Z upon dou X. So if I put the value of UZ and take a derivative, so what final answer I will get EXZ is equal to EZ is equal to minus B upon 4 pi Y upon X square plus Y square. So this is in the form of Cartesian coordinate. So now if I convert it into the polar coordinate, so I will get minus B upon 4 pi sine theta upon R. So this is the strain in the XZ and ZX direction. So now if I calculate for similarly for the strain in the YZ and ZY direction, so what we will get is ZY equal to EYZ equal to half of dou UZ upon dou Y plus dou UY upon dou Z. So this also becomes 0. So only we left with the dou UZ upon dou Y, and we'll get something, the term B upon 4 pi X upon X square plus Y square. And if I convert into the polar coordinate, B upon 4 pi, here we'll get cos theta upon R. So these are the engineering strains. So now if the engineering strains are very small, then we can say that these are equal to the true strain. So, if the strains are small, so epsilon xz equal to epsilon zx equal to exz equal to ezx. Similarly, epsilon yz equal to epsilon zy equal to eyz equal to ezy. And if you write a strain tensor for this screw dislocation, so we'll get a strain tensor something like this. So epsilon of s for screw dislocation, so it will be 0 0 exz 0 0 eyz ezx ezy equal to 0. So this is the strain tensor for a screw dislocation. Dislocation. Now, if you want to find out the stress for the screw dislocation stress field, so we know the relation, that is sigma ij equal to 2 times g into 2 times g into epsilon ij. So now, based on this equation, if I write, so the sigma xx equal to sigma yy equal to sigma zz equal to sigma xy equal to sigma yx equal to 0. Only the stresses will be acting in the sigma yz and sigma zy and sigma xz and sigma zx direction. So based on this equation, so I can write sigma yz equal to sigma zx equal to gb upon 2 pi cos theta by r. So here the equation was b upon 4 pi cos theta upon r. So if we multiply it with the 2 and g, so we'll get a that 2 by 2 get cancelled, 2 by 4, so it will be the 1 by 2, and this is the simplified version. This is the simplification of that equation. So similarly, sigma xz equal to sigma zx equal to minus gb upon 2 pi into sin theta upon r. So these are the stresses that we got for the screw dislocation. So if I draw the if I plot write down the stress tensor for a screw dislocation, so it will be something like this. Zero zero sigma xz 0 sigma yz sigma zx sigma zy 0. So this is the stress tensor for a screw dislocation. So if I plot this equation using help of MATLAB or some other online graph plotting resources or tools, so I will get like the strain in xz direction or the stress in sigma xz will be something like this. Similarly here, okay, so we will get a stress distribution graph something like this, but these are not symmetrical. Why? Because we have used the Cartesian coordinate system, but if we plot it in the polar, we will get the symmetrical distribution of the stress. So I will write down here non-symmetrical because we used Cartesian coordinate for a cylindrical object. Okay. So this was about the stress and strain field for the screw dislocation. So now if we find out for using the same way for the edge dislocation, so we'll get an equation something like this. Stress and strain around edge dislocation. So we'll get an equation like sigma x is equal to minus gb upon 2 pi 1 minus mu y 3x square plus y square, and here x square plus y square whole square, and sigma yy is gb upon 2 pi 1 minus mu, where mu is the Poisson's ratio, y x square plus y square divided by x square plus y square whole square. Sorry, here it will be the x minus y square, and sigma xy will be gb upon 2 pi 1 minus mu into x upon x square minus y square x square plus y square whole square. And the sigma zz is nothing but mu into sigma xx plus sigma yy. So this will be equal to minus gb upon nu pi 1 minus nu into y upon x square plus y square. So now if I write down the stress tensor and strength tensor, so sigma for edge dislocation, that is sigma xx, sigma xy 0, sigma yx, sigma yy 0, 0, 0, sigma zz, and strain tensor for edge also the similar. So here you can do the quick observation, that is this tensor are the inverse of the stress tensor that we have derived for the screw dislocation. So now if I plot this equation on MATLAB or some online tools like Mathematica, so we'll get a profile like this, the distribution. This is for your sigma xx. This is our positive and this is our negative stress. Similarly for sigma yy, so we'll get so this will be our positive, this will be our negative. Let me change the color. So this will be the positive stresses, this will be the negative. Here it will be positive, negative, positive and negative. Similarly, if I plot for the sigma xy, the equation, that is the sigma xy, so I will get equation something, I will get a graph something like this. So here it will be positive and this is negative. Similarly, if I plot a stress distribution curve for the hydrostatic stress, so how will you get it? So it will look like something like this. So this is for sigma h, that is hydrostatic stresses. So this was all about the stress and strain around the screw and edge dislocation. So now after that we came to the concept known as the energy of dislocation. So remember, so forming of dislocation inside a crystal will associated with the some energy, and that energy of dislocation is given by, that is the elastic energy, summation of I equal to xyz, g equal to xyz, sigma ij epsilon ij into dv upon dl. This is the energy per unit length. So suppose this is my dislocation core. Okay, so some energy will be associated with it. So this energy that some distance away from the dislocation core is nothing but the elastic energy, and this is the energy of core. So the total energy of a dislocation will be, that is energy of total equal to energy of core plus elastic energy. So for the screw dislocation, it is given by energy of screw dislocation, that is ES equal to GB square upon 4 pi ln R upon R naught. And for the edge dislocation, that is energy EE equal to GB upon 4 pi 1 minus mu ln R upon R naught. And for most of the metals or the material, mu is equal to 1 by 3. For most of the material, mu equal to 1 by 3. So if I write the total energy, that is ET equal to E core plus E elastic. So GB square upon 4 pi, let's ln R upon R naught plus some term B. And if I write E total is equal to alpha GB square. So here that the term other than GB square is nothing but a alpha, and alpha usually ranges from 0.5 to 1.5. So here from this equation you can see that the G will be the constant, alpha will be the constant. The only variable is B. So ET is directly proportional to B square. So ET is directly proportional to B square. So then we so what are the things we can write? So the unit of energy in this case is joule per meter. So also the core energy cannot be modeled using the linear elastic equation. So here we have not model core energy, we have only model the elastic energy. Also, the core radius usually lies from B to 4B. The energy of the core is about the content of the total energy of the dislocation. So, energy of the core 1/10 of the total energy of the dislocation. So, and it here, as I already mentioned, as the is cost energy to put dislocation in a crystal, dislocation tends to have a as small as B. So if the B is small, the energy will be small. So easily we can put a dislocation. So let me change the color. So as it is important point, as it costs energy to put a dislocation in a crystal, dislocations tend to have as small b as possible. Okay, so as we are talking about the the b should be small, so that the energy of the dislocation will be less. So by considering this concept, we can also say that dislocation can be conserved, like the dislocation can be branched into two separate dislocations. So in that case, if the energy of that two dislocation is less than the single dislocation, then it will try to favor that one. So it will try to branch out in the two dislocations. So let's say this is the dislocation one, B1, and it is branching out in two other dislocation, B2 and B3. So if B1, if energy of this combined two dislocation is less than the single dislocation, so it will try to means it will try to branch it out. So it will try to produce a partial dislocation. So this is the thing we have covered in the energy of a dislocation. Then similarly, we have calculated the energy for mixed dislocation. Energy for mixed dislocation. So in mixed dislocation, what will be the case? In one case, Burgers vector will be parallel to line vector, and in one case, it will be perpendicular to the line vector. So if we resolve it out and take a component and put it in the equation, that is E elastic is equal to E of H plus E of screw. So E of mixed dislocation, we can write GB square upon 4 pi sine square theta upon 1 minus mu plus cos square theta ln r upon r naught. Okay, so this is the energy for mixed dislocation. So then after this, we have seen the concept, that is the line tension of dislocation. So the line tension of dislocation. Suppose if we increase the length of a dislocation, then the increase in then that will cause the increase in the energy of a dislocation. As we already talked, the dislocations try to minimize B as much as possible. So increase in length of a dislocation will increase the in energy of a dislocation. Similarly, so if the dislocation energy is increasing, then any system will like to minimize that energy. Okay, it will try to minimize that energy. So therefore there will be some force or tension which will disallow it from the increasing. So there will be some resistance will be offered, so which will not allow it to increase its length or the size of dislocation. So if you want to change its curvature or change its length, then then we need to apply a stress or tension in such a way that it should overcome that line tension caused by that dislocation. So this is in brief about the line of dislocation. So, just a second. So increase in length of dislocation will cause increases energy of dislocation. So it will increase the energy of dislocation, and any system will try to minimize this energy. So therefore there will be a force or tension which will disallow it from increasing. So then we need to, if we want to change its curvature or length, it will have to overcome that line tension. Okay, so it will have to overcome that line tension. So suppose here, let's say this is the dislocation curve with a radius r. Let's say, suppose this is my angle del theta. So if I draw, so this will be del theta by 2. This is also del theta by 2. So this will produce some tension, like let's say this is T. So if we resolve it, so we'll get the tension here is T sine d theta by 2, and here also T sine d theta by 2. Let's say here we have applied some shear stress tau. Okay, and this whole length, let's see, this whole length is dl. So the tension or the force is nothing but a alpha gb square. Why is it so? Because energy per unit length is force. Okay, so if we try to balance out the forces, so here on the left hand side we are getting 2t sine theta, 2t sine del theta by 2, and it is balanced by this shear force, that is tau into b into dl. Okay, so this tau is nothing but t by b d theta upon dl, and this term, this whole term is nothing but 1 upon r, and tension is nothing but a energy. So we can write that tau equal to alpha gb square by b into r. This will give the alpha GB by R. So this is the shear stress required to bend uh, means to curve a dislocation. So, let me write down. This equation is the internal or external shear stress required to make a radius R in a dislocation. Okay. So this is about the line tension. Then we have seen the concept of glide of dislocation. So in glide of dislocation, we have seen that in the S dislocation, the glide plane is uniquely defined. By Burgess vector and the line vector. Where in case of screw dislocation, it is B and U are parallel, so not unique. And there are other factors also. Okay. So this was all about the last week. So this many things we have covered in the last week content. So now we will move towards solving some problems. So here are some concept related questions. So the first question is like this: when an 1 bar 1 0 a by 2 1 bar 1 0 dissociate into two dislocation, 1 by 6 2 bar 1 1 and a by 6 1 bar 2 1 bar, on what 1 1 plane must be the partial dislocation line. So please try to answer this, guys. So what they are saying, so suppose this is one plane, this is B1, this is B2 and B3. So B1 is A by 2 1 bar 1 0, B2 is A by 6 2 bar 1 1, and B3 is A by 6 1 bar 2 1 bar, and they are asking on what 1 1 1 plane must the dislocation will lie. So try to answer. So to solve this question, we need to try all the possibilities, and as these are lying on the some 1 1 plane, so this dot product should be 0. So what I'm trying to say is that, like, suppose this is B2 into XYZ should be 0 and B3 into XYZ. So then we can find out the plane. So how many planes are there in one family? So we have 4 planes. 3 and 1 to 4. So what are those? 1 bar 1 1, 1 bar 1, 1 1 1 bar and 1 1 1. So now this plane, that is 1 bar 1 1, 1 1 bar 1, 1 1 1 bar and 1 1 1. So put it in the place of XYZ and find out for which of these 4 the dot product becomes 0. So if I write B2 so we'll do it for 3. So here it's B2 and here we'll do it for B3. So B2 is how much? First is 2 bar 1 1 into 1 bar 1 1. How much is the answer? So it comes out to be 0. That is minus 2 plus 1 plus 1. Yeah, it's 0. But for B3 is 1 bar 2 1 bar and this is 1 bar 1 1. So this 1 bar is equal to 1. This is 2 3 and this comes out 2. So this plane is, that is for B3 and B2 and B3, it is not 0. So this can't be the answer. Similarly, try for 1 bar 1. Here also, if you try, you will not get a 0. Similarly, for this one, you will not get 0. Then only for this 1 1 1, you will get a 0. That is like if I put B2 into 1 1 1, that is 2 bar 1 1 into 1 1 1. So you will get a 0. Similarly here 1 bar 2 1 bar into 1 1 1 equal to 0. So B2 and B3 is 0 for only 1 1 1 plane. So the correct answer will be the 1 1 1 plane. This will be our correct answer. So this partial dislocation will lie on a 1 1 1 plane. So this was just a simple question. Now try to find out the the second question is like this. Consider the reactions between parallel dislocation given here. In each case, write the Burgers vector of the product dislocation and determine whether the reaction is energetically favorable or not. Please try to answer it, guys. So what they are asking, the third Burgers vector is summation of our first two. So first find out the Burgers vector for each condition. Then if the reaction is feasible or not, then what is the criteria? That is, energy should be minimum. And we know the energy is directly proportional to B square. So for which condition B square comes out to be less, that will be the physical reaction. So let's say this is our B1, this is our B2, and this is our B3. First, calculate the B3 for each condition. So for first condition, the B3 will be 2, 0, 0. Second condition, it will be 1, 1, 1. And for third condition, it will be 1, 1, 1. And for third condition, it will be 2, 1 bar, 1. So this is B2, this is the B3 for all three conditions. So now we know energy is directly proportional to B square. Then if B1 square plus B2 square is greater than B3 square, then it is energetically favorable. So now we need to find out the B1 square plus B2 square for all these conditions. So first we will take A. In A, B1 is A by 2, 1, 1 bar 0. And B1 square is A square by 2. Okay. And B2 is A by 2, 1, 1, 0. And B2 square is A square by 2. So B1 plus B2 square comes out to be A square. And B3 square is how much? It's A by 2, A by 2, A by 2. So A square by 4. A square by 2. Sorry. This comes out to be only A square. A square. So since B1 square plus B2 square is equal to B3 square. So this reaction will not be energetically favorable. So not favorable. So now do similar for B condition. So for B, B1 is A by 2, 1, 0, 1. and b1 square is a square by 2. Similarly, b2 is how much? b2 equal to a by 2, 0, 1, 1. So b2 square is also a square by 2. So b1 square plus b2 square equal to a square. Similarly, if we do for the b3 is how much? b3 is a by 2, 1, 1, 1. So how much? It is b3 is equal to 3a by 4. Since b1 square plus b2 square is greater than b3 square, so it is energetically favorable. So this is energetically favorable. Now do same thing for the third case, that is C. The B1 is given as A by 2, 1, 1 bar 0. So B1 is A square by 2. B2 is given as A by 2, 1, 0, 1. So B2 square is again A square by 2. Now B1 square plus B2 square is how much? It's A square. Now do for B3. B3 is how much? A by 2, 2, 1 bar 1. And B3 square is six A by 4, 3 by 2, A square. So again, here in this case, B1 square plus B3 square is less than B1 square plus B2 square is less than B3 square. So this will not be energetically favorable. Not energetically favorable. Okay. So this was the answer for first question. The second question. Now try to answer this question. A non-planar dislocation loop is shown in the figure below. All the dislocation segments are parallel or perpendicular to the coordinate axis shown. The segment label LA is a positive edge dislocation. So they are asking the character of segment CD, DE, EF and FG are screw or edge. So S is for the screw and E is for the edge. So please try to answer this, guys. So in this question, we need two important points. One is from the fundamental characteristics, and one is the how we identify whether it is a screw dislocation and edge dislocation. So the first thing, that we need to remember is that Berger vector for a given dislocation remains constant irrespective of the orientation of dislocation. This is first thing. Second thing, if our line vector is perpendicular to the Berger's vector, then this is edge dislocation. And if U is parallel to, and if U is parallel to Berger's vector, then it is screw dislocation. So they are asking us whether the character of CD, DE, EF and FG okay. So here you can see that this is the direction of Berger's vector given. Okay, and this is our line vector. Okay, so I will draw. This is the line vector that I am highlighting in the blue. Okay. So this blue one is our line vector. Okay. So now try to solve this. So here first we will draw the line vector at each segment. So this is the Berger's vector. Here also Berger's vector is like this. Here also it is like this. Here also it is like this. Here also it is like this. Here it is like this. Like this. And here also it is like this. And here. Okay. So this is the Berger's vector. So now we'll draw line vector. So I will use a green color. So this is the line vector. This is 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 line vector. So these are the green ones are the line vectors. So I'll write here. Red are Berger's vector, green are line vector. So now they are asking us for the first element is the CD. So here at CD, you can see that CD U is parallel to B. So this is screw dislocation. Now at DE, so here this segment is DE. At DE, U is perpendicular to B. So this is edge dislocation. Okay. Now at E and F. Okay. So now here at E and F. So at E and F, U is parallel to B. So this is again screw. Now they are asking at F and G. So at this F and G, U vector is perpendicular to B. So this is edge dislocation. So among this AC, AC. So here only this first option is matching with our answer. So this is the correct answer. That is screw edge, screw edge. So remember the Berger vector for a given dislocation remains constant irrespective of the orientation of the dislocation. If line vector and Burgess vector are perpendicular, then that dislocation is edge dislocation. If they are parallel, then that's screw dislocation. So for more reference, you can use imperfection in crystalline solid by means Nix and Kai or William Husford, Mechanical Behavior of Materials by William Husford. So now we'll try to solve next question. The question is that the edge dislocation cannot cross slip on different planes. So reason being the Berger vector for edge dislocation lies perpendicular to the dislocation line. So this in the very recent, like in the dislocation, glide of dislocation we have covered. So how the edge dislocation glides and how the screw dislocation. So what are the things that defines the slip plane for the edge dislocation and screw dislocation? So please refer to that notes and you can easily answer. So in the glide of dislocation, we have seen that the edge dislocation cannot cross slip on a different place. Why? Because it is uniquely defined by the Burgers vector and the line vector. So for edge dislocation, it is uniquely defined by and Burgers vector. But in case of screw dislocation, the slip plane is not well defined. That is, as they are the Burgess vector and line vector are parallel, so it is not unique. So in this case, the assertion is true, and the reason that is given, it is also true. So we have the option that is both assertion and reason are false. So this cannot be the correct answer. Similarly, assertion is true, but the reason is false. This is also not correct. So both assertion and reasons are true, but the reason is not the correct explanation of the assertion. This is also wrong. So both the assertion and the reason are true, and the reason is the correct explanation of this assertion. So this is the correct one. So the correct answer will be this one. Both assertion and reasons are true, and the reason is correct explanation of the assertion. So now coming to the fifth question. Which of the following statement is not correct? The stress field increases as we go near the dislocation core. Region of an edge dislocation with extra half plane of atoms experience tensile stress, while those below the half plane experience compressive stress. stress field around the edge dislocation is not symmetric, while screw dislocation have a symmetric radial stress field. So for your better understanding, I'll draw the diagrams. So from that diagram, you can easily answer. Now try to answer. This is the extra plane. So here. Like this is the stress field for screw dislocation, and let's draw this. Okay, just try to answer it. So I will draw it later. So plus try to answer it. So what they are saying, the stress field increases as we go near to the dislocation plane. As we have already discussed in the recapitulation, that if we go near to the dislocation core, the stress field increases. So this is the correct answer. So and they are asking about the not correct. So this is correct. Okay. So similarly, they are asking, the second is, the region of edge dislocation with extra half plane atoms experience tensile, while those below half plane experience compressive state. So suppose if I have this is the plane, this is my crystal. If I adding the extra plane, so it will try to compress it out. So with the extra half plane, we will be having compressive stress, and here we will be having tensile. It is not correct, but they are asking for the not correct. So this will be our correct answer. Now let's check for third one. The stress field around edge dislocation is not symmetric, while the screw dislocation have symmetric radial stress field. So this is also this also we have discussed in the quick recapitulation. So moving towards next question. The question is like this: consider the following body-centered cubic dislocation reaction. So they are asking to prove that this reaction will occur. So please try to answer. We have already discussed, like for the reactions to be happen, to take place. So it should have a minimum energy. So now you guys and try to answer it. So let's say this is our LHS and this is our RHS. Now try to answer. So as we know, energy is directly proportional to B square. So this reaction will occur only if LHS, energy of LHS is greater than energy of RHS. So let's say this is B4, B1, B2, B3. So if B4 square is greater than B1 square plus B2 square plus B3 square, that reaction, then only reaction will occur. So let me divide the section. So here we have B4 as A by 2, 1 bar, 1 bar, 1. So B4 square will come out to be 3A square by 4. Is it not? Now try to answer for other cases also. Let's say B1. B1 is how much? A2, A by 8, 1, 1, 0. So B1 square will be how much? So it will be A square by 32. Similarly, B2 is A by 4, 1, 1, 2. So B2 square will be 3A square by 8. Similarly, B3 is A by 8, 1 bar, 1 bar, 0. So the B3 square is how much? A square by 32. So now if we take B1 plus B2 plus B3 square, so what it will be? So let's say this is RHS. So RHS equal to A square upon 32 plus 3A square by 8 plus A square by 32. So if I solve, RHS comes out to be 7A square by 16. Okay, and this is my LHS. So here you can see that LHS is greater than RHS, or in other words, B4 square is greater than B1 square plus B2 square plus B3 square. So this reaction will happen. So let me write down the note. The energy is lower after reaction and therefore the reaction will okay. Now the next question, show that the reaction is the so they are asking whether the given reaction is energetically favorable or not. So you need to solve it same as our previous problem. So please try to answer it. Let's say this is B3, this is B1, and this is B2. Please try to answer it. B1, sorry, let's say this is B1, B2, and B3. So if B1 square is greater than B2 square plus B3 square, reaction energetically favorable. Now try to answer it. So we have B1 as A by 2, 101, 101 bar. So this gives us B1 square as A square by 2. Similarly, we have B2 as A by 6, 211, 211 bar. So this gives us B2 square as A square by 6. Similarly, B3 is A by 6, 112 bar. So B3 square will be A square by 6. So B2 square plus B3 square will be A square by 6 plus A square by 6. This will be A square by 3. So here from this 2, 1 and 2. From this 1 and 2, you can see that the B1 square is greater than B2 square plus B3 square. So the reaction is energetically favorable. So it is energetically favorable. Okay. So here we have the next question as the Burgess vector of dislocation is 0.25 nanometer in a crystal. The shear modulus is 40 GPa. Estimate the dislocation energy per unit length in the crystal. In this crystal. Please try to answer it. It's very simple. Just one formula and you will get the answer. we have the Burgers vector given B equal to 0.25 nanometer or 2.5 into 10 to the power minus 10 meter. Okay, the shear modulus, that is G, is 40 GPa or 40 into 10 to the power 9 Pascal. And what they are asking? They are asking us the E, energy of this location. So we know A energy is given by alpha GB square. So here only alpha is not given, but we know alpha lies from 0.5 to 1.5. So assume alpha equal to 0.5 and try to solve this. So here E is equal to 0.5 into G is how much? 40 into 10 to the power 9 into B square is how much? 2.5 into 10 to the power minus 10 whole square. So E comes out to be 1.25 into 10 to the power minus 9 joule per meter. So this is the dislocation energy per unit length in this. So just a simple question. So now consider the following dislocation reaction in centrifugal material. Whether it is energetically favorable. The same question again. Try to answer it. Okay. So please take a screenshot of this question, or you can take a photo, or you can just write down and try to answer it. In tomorrow's session, in next session we will discuss whether this is energetically favorable or not. Or should we solve here? Okay, we'll solve it here itself, today itself. So try it. So let's say this is our B1, this is B2, this is B3. If B1 square is greater than B2 square plus B3 square, then it is energetically favorable, right? So here we have B1 as A by 2, 1 bar 0. So if we take a B1 square, so we'll get A square by 2. Now we have B2 as A by 6, 2 bar 1. So if we take a B2 square, we will get A square by 6. Similarly, we have B3 as A by 6, 1, 2 bar, 1 bar. And we'll get B3 square as also A square by 6. Since B2 square plus B3 square is B1 square is greater than B2 square plus B3 square. So that is a square by 2 is greater than a square by 3. So this reaction is energetically favorable. Okay, this was just a simple answer. Now we have the next question is, in a copper, G is 48.3 GPa and the Burgers vector is taken to be 0.25 nanometer. So, and they are asking, so force required to bend the dislocation into a radius are equal to 10 micrometer. So here you need to use the equation for line tension and you will get an answer. So please try to answer it. It's very simple, guys. You try to answer it, you'll get an answer. So what they are saying, like there is a dislocation straight dislocation is there, and if you want to bend it in a R equal to 10 micrometer. So here some tension will be there. Okay, so they are asking what force F is needed to bend that dislocation into a radius of R equal to 10 micrometer. So here the we'll write down the given data first. G is equal to 48.3 GPa or 48.3 into 10 to the power 9 Pascal. Similarly, Burgers vector is also given, that is 0.25 nanometer or 2.5 into 10 to the power minus 10 meter. And they are asking us the force. So this line will produce some tension. Okay, so this is g theta by 2 as it is g theta. Okay, so it will give some tension t sine d theta by 2, and here also t sine d theta by 2, and here some force will be acting, that is nothing but tau is equal to, so this force is nothing but to the stress into the area, that is tau into B. Okay, so we know that F is equal to tau into B. So F is nothing but the tau, we know how much it is, or the tau is given by the equation alpha GB by R into B. Okay, so here also assume alpha equal to 1 by 2 or 0.5. Now try to answer it. F equal to 1 by 2 into G is how much? Is 48.3 into 10 to the power 9 upon R is how much? Is 10 into 10 to the power minus 6. Here I will write 10 equal to 10 micrometer or 10 into 10 to the power minus 6 into B square. B square is how much? 2.5 into 10 to the power minus 10 square. Now try to answer it. So you will get F somewhere around 1.5 into 10 to the power minus 4 Newton per meter. So this much force is required to bend the dislocation into a radius of 10 micrometer. So with this question, we will wind up our today's session here itself. If you have any doubt, you can ask. So we'll wind up our session here itself. So thank you for attending it, and thank you everyone. So I will close the session now.